Okay, so continuing on with page 4, we have number 3. I changed up the problem a little bit because the previous version of it didn't make sense. So I'll update the file that this came from. But I drew the diagram corresponding with this information. So we have quadrilateral ABCD with bases. If it's going to be a trapezoid, those bases need to be parallel, AB and CD. We also know that DA is congruent to CB. And by the way, even though I'm fixing these typos, or I'm stating that I'm going to fix them, doesn't mean I'm actually going to fix them. So I'm still taking these typos as bonus opportunities. All right, so submit them for your bonus credit. So CDB is congruent to angle ABD. All right, so all of that was marked up in the diagram. We, just like the last problem, we don't know that this is actually in the real world going to end up being a trapezoid, but because this is for academic purposes, we know that it's going to play out that way, so we could assume certain things. All right, is it going to end up being a perfect isosceles trapezoid? Probably not. Maybe not in all cases, but what else are you going to draw? You can draw it any way you want, but the default is usually to draw the thing that comes to mind. So that's what I did, and so here we go. So this information is given to us. It's pretty crystal clear. I mean, one thing you might want to consider thinking about when you're trying to prove something about a quadrilateral is the triangles, whether or not they're congruent. A little tip, like in number 2, those triangles look like they were congruent. If the triangles don't look like they're congruent, they're not going to be congruent. Right? Assuming that you've drawn something that's remotely, even close to what it's supposed to be, it will not be deceiving. All right. Also, if you tried to prove these two triangles congruent, it's not going to play out, because the best you could do is come up with the reflexive side here, in which case you're going to come up with the SSA or ASS, which is not an axiom. It's not a method for proving two triangles congruent. So that's out. But what we can do immediately is show that CD is parallel to AB, right? And so here we're going to kind of dig deep. AB is parallel to CD if two lines are cut by a transversal and the alternate interior angles are congruent, then the lines are parallel. All right, so that's pretty nice. I mean, it's a blast from the past, but useful, definitely. All right, so I'm going to mark it up, and this is how I mark up, and most people too, mark up parallel on a figure. So we're there. This was a two-stepper. I never count the given. All right, so trapezoid ABCD, a quadrilateral with at least one pair of opposite parallel sides. They'd have to be opposite in order to be parallel, but we say it anyway. Is a trapezoid. So it actually allows for the fact that you could have more than one pair of opposite parallel sides, which goes back to the diagram on the first page. All right, I'm going to flip back to that now. Because the table at the bottom is nice, but I think the flow chart is better, because if you start off with quadrilaterals, you're following the flow, you can see that the first thing you get to, aside from the kite's the outlier, is the trapezoid. And then everything springs outward from the trapezoid. You can get a parallelogram if another pair of opposite sides are parallel. Or if the two legs are congruent, like we have here, it would be isosceles trapezoid. They didn't ask us for that, but that's okay. It's another consequence. Then from there, we can follow the path. So let's say we follow the path to parallelogram. From parallelogram, we can get to a rectangle, or we can get to a rhombus. That little stem didn't end up being everything I had hoped. All right. We could also get to the path of rectangle, or get to a rectangle by following the path. The first highlighter came out great. Now it's all like shaky and wonky. By following through the isosceles trapezoid, we can get to a rectangle that way. And then from there, we can follow the path to a square. But basically all roads lead to Rome, a square. And so there we are. All right. But I think that diagram ends up being more useful than this table. All right. And besides, who wants to memorize all this? All right. So we have it. And now let's move on. Two more. Given parallelogram, prove parallelogram. All right. Well, the good news is there's less to write in the given. Hopefully by now we're starting to realize that that's actually not good news. Less to write in the given means less given information, which means more stuff that you have to figure out on your own. I'd rather the writer's crap. Sometimes. All right. So BF is congruent to DE. And we know the whole shabiggity bangity boom here is a parallelogram. And we need to prove that FCEA is also a parallelogram. And so we have different avenues. Opposite sides being parallel, diagonals bisecting each other, opposite sides being congruent. You got to think about that. Is that something that's going to work? All right. Well, what kind of figure will you have if opposite sides are congruent? All right. So, could it be a square? Well, a square is a type of parallelogram. Could it be a rectangle? Well, a rectangle is a type of parallelogram. Could it be a rhombus? A rhombus is a type of parallelogram. All right. Could it be an isosceles trapezoid? No. All right. Not necessarily. All right. It's not in and of itself, or a trapezoid itself, because those wouldn't have opposite sides being parallel. All right. So, if we could show that the opposite sides are congruent, then we will have shown that it is a parallelogram. All right. So that's the road I think that we should take. So let's get to it. First thing, we are working with the fact that the entire figure is itself a parallelogram, and we know some information about that. So opposite sides of that entire figure are going to be congruent, and opposite angles are going to be congruent. So I know angle B and angle D are going to be the same. And AB and CD are going to be the same. All right, this, I kind of pretend like it's laziness, but in my mind, I think of it as cleverness. Combining them into one step. In a parallelogram, opposite sides and angles are congruent. All right. So we already knew that BF and DE were congruent. I can now state that ABF and DCE are congruent, which is great. All right, so ABF and ABF and CDE. Just want to get the ordering right. And that's the SAS axiom. All right. Through that information, going purple for those keeping score at home, I can now state that AF and CE are congruent. And that's because corresponding parts of congruent triangles are congruent. CPCTC. All right, so I got one pair of opposite congruent sides of a quadrilateral. That's great. Now I just need the other pair. Now I do know that the whole mamma jamma here, BC and AD are congruent for the same reason that AB and CD were congruent. So retroactively, I'm going to retcon this baby. AD, BC are congruent. All right, so that'll be an Easter egg for this video. Send me the definition. I actually know this, and so I want to share the wealth. I would like the definition of the term retcon, R-E-T-C-O-N, and also an example of something being retconned in your favorite TV show, movie, something along those lines. So definition of retcon and an example of retcon in use, all right, for a bonus point. That is the Easter egg for this video. So I know those two pieces of information, and so therefore I can use subtraction to show that AE and CF are congruent. All right, so I can now state that AD minus DE is congruent. Well, you know what? I'm going to actually make the statement first that that's congruent to AE. And that BC minus BF is congruent to CF. Therefore, AE congruent to CF. And that's the subtraction postulate. And so now I have these two guys. So now I could say parallelogram FCEA. In a quadrilateral, if opposite sides are congruent, it is a parallelogram. All right, very shorthandy in terms of the notation, but it's either that or it ends up being an essay, and I don't want that to be the case for either of us. I don't want to have to write it, and I don't want to have to read yours because my attention span doesn't allow for me need to, what was I saying? Number 5, rhombus ABCD. So I'm going to jot that down. We also know that AF congruent to DE. Und we know AE is congruent to the BF. And we need to prove that this bad boy is a square. This bad boy is a square. Alright, so ABCD, AFDE. Where's my DE? Oh, this whole shibiggity bangity boomity bangity bombity boom 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 boom. Okay. This guy right meow, and this guy right about meow. Alright. So somehow we gotta prove this is a square. That sounds exciting. Because it's a rhombus, we know that all sides are congruent. That's great news. So AB congruent to BC, congruent to CD, congruent to DA. In a rhombus, all sides are congruent. All right, so I'll put some tick marks here, here. You do it, well, sometimes we do it that way. It's not the most elegant thing in the world, but just a little reminder. All right, those 4 sides are congruent. All right, we know AF is, like I said, congruent to DE. All right. So, couple of possibilities. One possibility would be to prove right angles if it's going to be a square. Now, something to keep in mind, this figure doesn't look like a square, so my tendency is to say, well, it's probably not going to be, but we do have to keep in mind also that sometimes they, whoever they are, they do that. Right? They want us to, start questioning things. All right. These are not diagonals. So if we're going to prove that there's a square involved here for the whole thing, it's probably not going to have to do with diagonal relationships. All right. So we got to be thinking in terms of right angles, right triangles, and things along those lines. All right. So we know, again, that AF and DE are congruent, but we also know that AE, which I neglected, AE and BF are also congruent. I'm just trying to think how I want to denote that. 2 tick marks here and here. Okay, so it's hard to see, but what we just got out of this are 2 congruent triangles through the side, side, side axiom. All right, so we can make a note of that. So 3 is that, so the highlighted, those are 2 congruent sides. I got a couple of red single tick marks as, I mean, we'll call them hypotenuses, even though they're not necessarily right triangles, but they're the longer side. And then the 2 purple tick marks corresponding with AE and BF. So triangle ABF would be congruent to triangle DAE. Just making sure I'm denoting it the same way. Not that it really matters, but little consistency. So the SSS axiom. All right, so we have that, right, which tells us that we have some angles that we now know are congruent to one another. All right, so that's actually going to fix this whole thing. But in order to really kind of emphasize the whole point, what I'm going to do, let me just get a little kooky here. I'm going to take all this stuff here and just move it off on the side. Then I'm going to do my best to draw the entire parallelogram with my shaky, nerve-damaged handwriting. I'm going to actually do that again while putting the line draw tool on. All right, that's the best I can do. I'm going to snag that, drag it down here, put this stuff back. Yeah. Maybe I'll shrink this down a little bit because we'll believe that it's the same figure. It doesn't need to necessarily be the same size. So I'm going to label it A, B, C, D. Yeah, starting here. Okay, so from all of this, we've proved that these two angles are now congruent because of CPCTC, right? So I'm going to label that up. I'm going to say angle DAE is congruent to angle ABF. Either order is fine. And that's CPCTC. All right, so in my ancillary diagram, that's these two angles. All right, then I can state that angle DAE is congruent to angle C. All right, angle C could be nothing else, so that's easy enough. And angle ABF is congruent to angle, I'll call it ADC. And that's in a rhombus. Opposite angles are congruent. All right, so through substitution, we can now state that all four angles are congruent. All right, so I'm just going to name them all. Angle DAE is congruent to angle, that's not an angle symbol, ABF, which in turn, that was actually already given, all right? Not given, sorry, already figured out in CPCTC, but then DAE, we figured out was congruent to angle C, and we also figured out that angle ABF was congruent to angle ADC. And that's all just by substitution. All right. So, since all four angles are congruent and you have 360 degrees to play with, 360 degrees divided by four congruent angles, each one has to be 90 degrees. All right. So, we now know that we're dealing with a square, ABCD, and that's because a rhombus with four congruent angles is a square. So the lengthiest of the proofs and obviously the most difficult based on the number of steps, But if you look at the flow chart, you see that, like the further you work your way down the line, the more ingredients there are into the quadrilateral, the more things that you're going to have to prove. So it can be a little kooky when you start getting into the more particular types of figures. The more general it is, the easier it is to prove. If I said prove something is a quadrilateral, all you'd have to do is prove that there are four sides. All right. If I say prove that something is a parallelogram, it gets a little bit more complicated. Right. But really, it's just a matter of just trying to understand where these steps are coming from and going from there.